Welcome to Level 2 Physics, and begin with, we'll look at some mathematics that you're going to be using in the course to assist you. And with that in mind, we'll start with the idea of units. So how can you quantify a measurement? How can you measure a measurement? So if I'm measuring the length, for example, of a table, how can I quantify that measurement? Then I'm going to need something called a unit, and that unit has to be able to be shared and be common with other people. So when everyone says, I've measured my table in this unit, everyone knows what that means. So since we're talking about measuring tables, let's look at the unit for length. So units are essentially arbitrary as long as they're shared between people. So for length, we can also use the inches and the feet of the imperial system. But now we have moved on to the metric system, which was first developed in the late 18th century. So you can see, in terms of what a meter meant, or is, has evolved over time from this timeline. So in 1790, it was essentially the length of a pendulum that swings to the maximum over a 1 second time period. And then a year later, we moved on from that. We said, well, that's not very accurate or precise. So then became the length of 1/10,000,000th of a distance between the North Pole and the equator. And then 8 years later, we got fidgety with that again. 4 years later, we got fidgety with that again. And we said it's the distance of a particular official bar, which was kept in Paris. And then we obsessing with bars of metals. By 1799, the length of the official bar of platinum, which I've actually seen in the French National Archives in Paris, was defined as what a meter meant. And then by 1889, so that kept around for quite a long time, about 100 years, in 1889 it became the distance between two lines in an official bar, this time of platinum indium alloy, measured at 0 degrees Celsius, which makes sense in a sense, because in Paris, basically the length of a meter changed depending on what season it was, because in summer it expanded and in winter it contracted. And if it was kept at a core temperature, in this case 0 degrees Celsius, it meant the temperature and the length stayed a lot more constant as a standard. And then finally, in 1983, it's now the length travelled by light in a vacuum during 1/300th of a second, 300,000 millionth of a second, basically. And then that's now what our definition of a meter is. So it has changed. And that's an example of a standard. So we use the system known as System Internationale from the French, and it means that we've got to have a standard for each of our units to maintain consistency over time. And for example, there's a definition of a second. A second is defined as the interval required for, well, quite a number of vibrations, was it roughly 9 billion vibrations, of a cesium-133 isotope measured via an atomic beam clock. And this is now where the metric system comes in and the use of standard form. So when we drive to Nelson, for example, we don't say, well, I've driven 40,000 meters. We say 40,000 kilometers. And all that means is it's 4 times 10 to the 3 meters. It's essentially known as standard form. We tend to write our answers in that, especially when we're dealing with large or particularly small numbers. Rather than writing out each of the individual numbers, we use standard form to kind of simplify it. So for example, if we're dealing with the distances in space, we could use a petameter, which is 1 times 10 to the 15. Or if we're dealing with the really small sizes of atoms, then rather than writing out all those zeros, 0.0000 on, we use something called like picometers or femtometers. So a picometer would be 1 times 10 to the negative 12 meters. And we'll look at those in class in more detail. Yeah, so the value given in a number is the number of places the decimal place actually moves. So make sure you go in the correct direction. You don't want to be saying the distances involved in bacteria are 1 billion meters. It's 1 times 10 to the negative 9 meters if we're dealing with the nanoscale. There we go. So 900 nanometers is 900 times 10 to the 9 meters. And 900 nanometers is 0 and 9 zeros difference, decimal point, meters. Okay, so that's how you interconvert using standard form. And finally, there's a lot more. You don't have to really learn those so much. Basically, if you fit between 1 times 10 to the 12 and 1 times 10 to the negative 12, learn those suffixes. We say, for example, what I mean by suffix is a centimeter, then centi is the suffix, 1 times 10 to the negative 2 meters, then you'll be fine for level 2 physics. So those, or that is a basic introduction to units.